Imagine a machine born in pure fire, a colossal white dart strapped to a controlled explosion, climbing to orbit on a pillar of furious, ground-shaking power. Now, imagine that very same machine returning home weeks later, not with a roar, but in a profound and total silence. An unpowered 100-ton glider, gracefully falling out of the blackness of space, a brick with wings aimed at a single perfect runway on the curve of the Earth. This was the strange, beautiful, and deeply flawed paradox of the Space Shuttle. For 30 years, it was humanity's bridge to the stars. It was more complex than any machine ever built, a triumphant and sometimes tragic symbol of our ambition to tame the frontier of space. Our story begins in the late 1960s, in the triumphant afterglow of the Apollo program. We had reached the moon. The question now was, what next? The Apollo missions were incredible feats, but they were also monumentally expensive and unsustainable. The Saturn V rocket, a machine of breathtaking power, was a single-use vehicle. Every time we went to the moon, we had to throw away the most powerful rocket ever built. It was like driving from New York to Los Angeles and throwing away the car when you arrived. NASA dreamed of a different future, a future where space was not a place for rare, heroic expeditions, but a place for routine work and travel. They dreamed of a space truck, a vehicle that could launch like a rocket, carry people and cargo to an orbiting space station, and then return to Earth and land on a runway like an airplane, ready to be refueled and flown again, perhaps every few weeks. This was the dream of the Space Transportation System, or STS, the dream of making spaceflight routine, affordable, and safe. And the heart of this dream was a beautiful, winged, reusable spaceplane.
The early concepts for this spaceplane, from the late 1960s, were truly a vision of the future. They looked like something straight out of science fiction. The most popular designs were for a fully reusable two-stage system. You would have a massive, winged booster plane, about the size of a 747, with a smaller, winged orbiter spacecraft riding on its back. This giant duo would take off from a runway like a plane, climb to the edge of the atmosphere, and then the orbiter would detach and fire its own engines to continue into orbit. The giant booster plane, with its own human pilots, would then fly back and land at the launch site, ready to be refueled for the next mission. It was a beautiful, elegant, and incredibly ambitious vision. It was a vision of a true spaceliner. But it was also a vision that was fantastically, prohibitively expensive. As NASA's budget was slashed in the post-Apollo era, and as the political will for grand, costly space projects faded, this beautiful dream began to collide with the hard wall of reality. The story of the Space Shuttle's design is, in many ways, a quiet story of painful but necessary compromises. The fully reusable flyback booster was the first part of the dream to die. It was simply too technologically complex and too expensive to develop. So the engineers went back to the drawing board. How could they get a winged orbiter into space without it? The solution they settled on was a strange, asymmetrical, and uniquely iconic design. The orbiter would still be there, but instead of riding on the back of a reusable plane, it would be strapped to the side of a large, disposable fuel tank with two powerful rockets strapped to the sides of that. It was a far cry from the sleek spaceliner of the original dream. It was a compromise, a hybrid of reusable and disposable parts, a brilliant but slightly awkward solution born from the harsh realities of politics and budgets.
Let's look more closely at these compromises, because they define the very nature of the space shuttle we came to know. The first great compromise was that giant, rust-colored fuel tank. This was the external tank, or ET. It was, in essence, the fuel tank for the orbiter's own three main engines. It was filled with over 700,000 kilograms of super cold liquid hydrogen and liquid oxygen. During the launch, it fed all this propellant to the orbiter's engines, but once it was empty, just before reaching orbit, it would be jettisoned. It was the only major part of the shuttle system that was not reusable. It would fall back to Earth, burning up in the atmosphere over a remote stretch of the Pacific or Indian Ocean. It was a necessary sacrifice to save the immense weight of carrying the empty tank all the way to orbit and back. The second and much more controversial compromise was the choice of boosters. Instead of a liquid-fueled, controllable first stage, NASA, under intense pressure to lower costs and to use contractors from specific states, opted for 2 solid rocket boosters, or SRBs. These were, for all intents and purposes, the 2 largest, most powerful firecrackers ever built. They were huge, segmented rockets filled with a solid, rubbery propellant. They provided the main thrust for the first 2 minutes of flight, getting the entire heavy stack off the ground. The advantage of SRBs was that they were relatively simple and provided immense power. The disadvantage was profound. Once you light a solid rocket, you cannot turn it off. From the moment of ignition, the shuttle was committed to a 2-minute ride of controlled, violent fury. There was no abort option on the launch pad. This lack of control, this all-or-nothing design, was a compromise that would, decades later, have tragic and devastating consequences. These 2 compromises, the disposable tank and the solid boosters, defined the strange 3-part vehicle that would become one of the most iconic machines in human history.
Now, let's take a quiet, detailed tour of the star of the show, the orbiter vehicle itself. This was the part that was a spaceship, a science lab, a cargo truck, and a glider, all rolled into one. Let's start with its skin, the thermal protection system. This was the shuttle's shield against the incredible heat of re-entry. Unlike the old Apollo capsules, which used a single ablative heat shield that burned away, the shuttle needed a reusable system. The solution was an incredible, painstaking mosaic of thousands of individual, lightweight silica tiles. There were over 24,000 of these tiles on each orbiter, and almost every single one was a unique shape, custom-made to fit its specific location on the vehicle. These tiles were, in essence, made of a very pure, very lightweight glass foam. They were incredibly good at insulating against heat. You could heat one side of a tile with a blowtorch until it was glowing red hot, and you could still pick it up by the edges with your bare hands. But they were also incredibly fragile. You could famously dent one just by poking it too hard, which is not exactly what you want on a vehicle designed to re-enter the atmosphere like a meteor. Each tile had to be individually glued to the shuttle's aluminum frame, a process that was incredibly labor-intensive. And after every single flight, the entire orbiter had to be meticulously inspected, and hundreds of tiles had to be repaired or replaced. For the areas of the most intense heat, like the nose cone and the leading edges of the wings, a different, even more robust material was needed. This was reinforced carbon-carbon, or RCC. It was a composite material that was incredibly strong and could withstand the highest temperatures of re-entry. It was the quiet gray armor that protected the shuttle's most vulnerable points. The delicate, beautiful, and sometimes tragically fragile skin of the orbiter was one of its greatest engineering triumphs, and ultimately, one of its greatest weaknesses.
Now let's consider the orbiter's shape. With its graceful delta wings and its tall tail fin, it looked like a futuristic airplane, but its appearance was a little deceptive. It was a very, very poor glider. Its nickname among pilots was the Flying Brick. Because it was so heavy and its wings were relatively short, it had a glide ratio of about 4.5 to 1. This means that for every 4.5 feet it traveled forward, it dropped 1 foot in altitude. A modern sailplane might have a glide ratio of 50 to 1 or more. This meant that the shuttle's descent from orbit was incredibly steep and incredibly fast. Once it committed to its final approach, it had only one chance to get the landing right. It had no engines to power it on its final approach. It was a 100-ton unpowered glider. The commander had to perform a series of precise, banking turns to bleed off speed, all while perfectly managing the vehicle's energy to arrive at the runway at the exact right altitude and speed. The final approach was much steeper and much faster than that of a commercial airliner. It was a quiet, controlled fall, a final, graceful display of pure piloting skill at the end of every single mission. What made the shuttle so unique and so useful was its immense payload bay. The two giant doors on the top of the orbiter would swing open in space to reveal a cargo bay that was 18 meters long and 4.5 meters wide, about the size of a school bus. This was the shuttle's reason for being. It could carry huge satellites into orbit and deploy them. It could carry entire laboratory modules, like the Space Lab module built by the European Space Agency. And most importantly, it was the only vehicle in the world capable of carrying the massive components needed to build the International Space Station. The payload bay was what turned the shuttle from just a spacecraft into a true orbital work truck.
And to move things around in that payload bay, the shuttle was equipped with one of its most iconic and elegant pieces of technology. This was the Canadarm. As its name suggests, it was a contribution from the Canadian Space Agency. It was a remote-controlled robotic arm, about 15 meters long, that was mounted on the side of the payload bay. It functioned very much like a human arm, with joints at the shoulder, elbow, and wrist, and a hand at the end called an end effector, which could grapple onto satellites and other objects. An astronaut inside the shuttle's aft flight deck would control the arm using a set of joysticks, watching what they were doing through the windows that looked out over the payload bay. The Canadarm was an incredibly precise and reliable piece of equipment. It was used to lift heavy satellites out of the payload bay and release them into orbit. It was used to capture satellites that needed repair and bring them into the bay for the astronauts to work on. And during spacewalks, it could be used as a mobile platform, with an astronaut attached to the end, moving them around like a cherry picker. The quiet, graceful, and surprisingly strong Canadarm was one of the most successful and essential tools of the entire Space Shuttle program. And finally, let's take a look inside the orbiter at the flight deck. The cockpit of the Space Shuttle is one of the most complex and fascinating control rooms ever created. It looks like a hybrid of an airplane cockpit and a science fiction spaceship. It was one of the very first vehicles to use a glass cockpit, meaning it had digital computer screens alongside the traditional analog dials and switches. The flight deck was a testament to the immense complexity of the vehicle. There were over 2,000 individual switches, dials, and circuit breakers on the control panels, each one with a specific function. The astronauts had to have an encyclopedic knowledge of this layout. The forward panel was for the commander and the pilot, primarily for flying the vehicle during ascent and landing. The aft flight deck, with its windows looking out into the payload bay, was for orbital operations, like controlling the Canadarm or managing experiments. It was a quiet, humming, and incredibly dense workspace, the human brain of this magnificent, complicated machine. All right, we've explored the incredible machine itself. Now let's imagine what it was actually like to live and work aboard it for a typical mission. Let's take a quiet, procedural journey through a week in the life of a space shuttle crew. Our journey begins, as all missions do, with the countdown and the ascent. In the final hours before a launch, the crew would be strapped into their seats on the shuttle's flight deck. The giant orange external tank would be filled with over 500,000 gallons of super-cold liquid oxygen and liquid hydrogen. The countdown would proceed, with thousands of checks being performed by the computers and the launch team on the ground. At about T-minus 6.6 seconds, the shuttle's 3 main engines would ignite in a staggered sequence, creating a deep, rumbling roar. The entire vehicle would pivot slightly, a motion the astronauts called the twang, as the engines powered up to full thrust. For these few seconds, the shuttle was held down on the launch pad by massive bolts. Then, at T0, came the moment of true violence and commitment. Two colossal explosions would happen, one on either side of the external tank. This was the ignition of the two solid rocket boosters. The SRBs provided the main push off the pad, and their ignition was an instantaneous, explosive event that created a kick in the pants for the crew. The hold-down bolts would explode away, and the entire 2,000-ton stack would leap off the launch pad, climbing on a pillar of controlled fire and steam. Just after clearing the tower, the shuttle would perform its famous roll program, a maneuver where it would roll over onto its back. It did this for aerodynamic and communication reasons, so that the orbiter was underneath the tank during its ascent. The ride for the next 2 minutes was a rough, shaky, powerful push from the two SRBs. Then the boosters would burn out, be jettisoned, and fall back to the ocean to be recovered and reused.
After the solid rocket boosters separated, the ride would become much, much smoother. For the next 6 minutes, the shuttle would continue to accelerate, pushed now only by its 3 quiet, efficient, liquid-fueled main engines. The astronauts would be pressed back into their seats by a steady force of about 3 Gs. Then, about 8.5 minutes after liftoff, after burning through 500,000 gallons of fuel, the main engines would shut down. And in that instant, everything would change. The immense G-forces would vanish. The roar and vibration would be replaced by a profound and perfect silence. Any dust or small objects in the cabin would suddenly lift up and begin to float. This was the moment of main engine cutoff, or MECO. It was the moment they had reached orbit. It was the moment they became weightless. Now begins the quiet, steady rhythm of life in orbit. The shuttle orbiter was a 2-level vehicle. The upstairs was the flight deck, the cockpit we've already described. The downstairs was the mid-deck, and this was the main living area for the crew. It was a small, windowless, cluttered space, but it was their home. The mid-deck contained the crew's sleep stations. These were essentially small bunks, just big enough for a person, with a sleeping bag tethered inside. An astronaut would zip themselves into the bag to keep from floating around and bumping into things while they slept. The mid-deck also contained the galley, which was the small, dedicated area for preparing food. It wasn't much of a kitchen. It had a rehydration station for freeze-dried food pouches and a small, suitcase-like convection oven for warming up the thermostabilized meals. There was no refrigerator and no freezer. The meals were functional, but a step down from the relative luxury of Skylab. And of course, the mid-deck was also home to the space toilet, the waste collection system. As we've discussed, it was a complex and sometimes temperamental machine that used airflow instead of water. Learning to use it correctly was a key part of every astronaut's training, and a quiet but constant part of daily life in orbit.
A typical day in orbit was a busy, highly scheduled affair, planned down to the minute by mission control. But the core of most shuttle missions was about working in space. The shuttle was, above all else, a versatile work truck, and it had 3 main jobs. The first was acting as a satellite delivery and repair service. Many of the most important satellites of the 1980s and 90s, including scientific observatories and communication satellites, were designed to be launched from the shuttle's payload bay. The crew would open the giant payload bay doors, and using either a spinning platform called a frisbee launcher or the Canadarm, they would gently release the satellite into its own orbit. Even more impressively, the shuttle could also capture satellites. If a satellite malfunctioned in orbit, the shuttle could fly up to it, and a spacewalking astronaut or the Canadarm could grapple it and bring it back into the payload bay for repairs. The most famous example of this was the Solar Max mission in 1984, where astronauts successfully repaired a satellite that had failed in orbit. This was a capability that no other spacecraft in the world possessed. The second major job was conducting science in the Space Lab module.
Spacelab was a large, pressurized laboratory built by the European Space Agency that could be fitted inside the shuttle's payload bay. It was connected to the crew cabin by a tunnel, allowing the astronauts to float inside and work in a comfortable shirt-sleeve environment. They would conduct hundreds of experiments in material science, fluid physics, and life sciences, taking advantage of the unique microgravity environment. And the third and most iconic job was performing spacewalks, or extravehicular activities, EVAs. The shuttle had its own airlock, allowing 2 astronauts at a time to venture out into the payload bay or to work on external structures. The process of a spacewalk was a long and quiet one, involving hours of pre-breathing pure oxygen to purge the nitrogen from their blood and prevent decompression sickness. Then they would step out into the void, tethered to the ship, their every move a slow, deliberate, and beautiful ballet.
For all its complexity and all the simple daily work of its missions, the Space Shuttle program was also responsible for some of the most stunning and important moments in the history of modern science. It was not just a truck, it was a repair vehicle, a construction platform, and a laboratory. In this next part of our story, we will explore the quiet triumphs that became the shuttle's most enduring legacy. We must begin with what is arguably the single greatest success story of the entire program, a mission of incredible daring and profound scientific importance. This is the story of how the shuttle and its astronauts saved the Hubble Space Telescope. The Hubble Space Telescope, launched in 1990 from the payload bay of the Space Shuttle Discovery, was meant to be our perfect, crystal-clear eye on the cosmos. It was the most expensive and most anticipated scientific instrument ever built. It was designed to see the universe free from the blurring, distorting effects of Earth's atmosphere. But when the first images came back from Hubble, the scientific community felt a collective wave of horror and disbelief. The images were blurry. They were out of focus. Something was terribly, terribly wrong. After a period of intense investigation, the cause was found. The telescope's main mirror, a beautiful 2.4-meter wide piece of glass polished to near perfection, had a flaw. It had been ground to the wrong shape. The error was almost infinitesimally small, about 1/50th the thickness of a human hair, but it was enough to cause a serious problem called spherical aberration. The telescope could not focus all the light it collected to a single sharp point. For a time, it seemed like the billion-dollar telescope was a catastrophic failure, a national embarrassment. But the beauty of Hubble and the genius of its design was that it was designed to be repaired in orbit by Space Shuttle astronauts. And so began one of the most audacious and complex repair missions ever conceived.
The plan to fix Hubble was a work of quiet optical genius. You couldn't, of course, bring the giant mirror back to Earth to be reground, so the engineers had to find a way to correct the flawed vision of the telescope while it was in orbit. The solution they came up with was essentially to give the telescope a tiny, incredibly precise pair of eyeglasses. This came in the form of an instrument called COSTAR, which stood for Corrective Optics Space Telescope Axial Replacement. It was a device about the size of a telephone booth, and it contained a series of small, specially shaped mirrors on articulating arms. The plan was to insert COSTAR into the telescope, and these small mirrors would pop out and intercept the blurry light from the main mirror, correcting its path before it reached the scientific instruments. In addition to COSTAR, the astronauts would also replace the telescope's main camera, the wide-field planetary camera, with a new, updated version that had its own built-in corrective optics. The entire plan required the astronauts to perform a series of incredibly complex and delicate tasks, essentially performing optical surgery on a school bus-sized satellite while wearing bulky, pressurized spacesuits and gloves. The mission chosen for this high-stakes repair job was STS-61,
aboard the Space Shuttle Endeavour, which launched in December of 1993. The crew was one of the most experienced ever assembled, and for 5 consecutive days, they conducted a series of 5 long and grueling spacewalks, the most ever attempted on a single mission at that time. Each day brought a new, incredibly difficult challenge, all of it performed against the silent, beautiful backdrop of the Earth turning below.
The first challenge of the Hubble repair mission was simply to capture the giant, delicate telescope. The shuttle, commanded by Richard Covey, had to perform a series of precise maneuvers to approach the Hubble without its thruster jets contaminating the telescope's sensitive optics. Then, using the long Canadarm, Swiss astronaut Claude Nicollier had to delicately grapple the 12-ton telescope and gently pull it into the shuttle's payload bay, where it was anchored for the repairs. The spacewalks that followed were a masterclass in quiet, focused, and sometimes frustrating work. The astronauts, working in pairs, faced numerous unexpected problems. Tiny, stripped screws refused to come loose. A set of solar panels warped in the sunlight and couldn't be retracted properly. At one point, a pair of astronauts had to physically, manually roll up one of the giant solar arrays like a stubborn carpet. The most difficult task was installing the new corrective optics. The astronaut Story Musgrave, on one of his spacewalks, had to open a set of small, delicate doors on the side of the telescope to install the COSTAR instrument. The doors were slightly warped from the temperature changes in space, and they wouldn't close properly. For long, tense minutes, he and his spacewalking partner Jeffrey Hoffman had to gently but firmly improvise a solution to get the doors latched. Their every move a quiet ballet of immense caution. Throughout the 5 spacewalks, the crew worked with a calm professionalism that was awe-inspiring. They successfully replaced the old camera, installed the COSTAR optics, replaced gyroscopes, and installed new solar panels. After 5 long days of the most complex in-orbit repair job ever attempted, they used the Canadarm to gently lift the repaired Hubble back up and release it into orbit. The entire world held its breath, waiting to see if their incredible work had paid off.
A few weeks later, on Christmas Eve of 1993, NASA released the first new images from the repaired telescope. And they were perfect. The blurry, disappointing smudges were gone, replaced by crystal-clear, razor-sharp images of distant galaxies and beautiful nebulae. The repair had been a complete and spectacular success. There was a wave of relief and pure joy that rippled through the scientific community and the public at large. The Hubble repair mission was, without a doubt, the Space Shuttle's finest hour. It showcased the vehicle's unique capabilities in a way no other mission could. It was a story of human ingenuity, of our ability to diagnose a complex problem from a distance, to invent a clever solution, and to send skilled human beings into a dangerous environment to fix it. It turned what could have been one of NASA's greatest failures into one of its most enduring triumphs, and it gave humanity a clear, beautiful new window on the universe. This ability to service and upgrade telescopes in orbit was a quiet but profound legacy of the shuttle. It would return to Hubble 4 more times over the years, with new crews installing even more advanced instruments, keeping the telescope at the forefront of science for over 3 decades. Now, let's turn to the shuttle's other great legacy, its role not as a repair vehicle, but as the primary construction vehicle for the largest and most complex structure ever built in space. This is the story of how the shuttle built the International Space Station. The dream of a permanent human outpost in orbit is an old one, but it was the Space Shuttle that finally made it possible. The International Space Station, or ISS, is a modular creation, a sprawling complex of laboratories, habitats, and trust structures that was assembled piece by piece in orbit over more than a decade. And the shuttle was the only vehicle in the world with a large enough cargo bay and a strong enough robotic arm to carry the huge components of the station into space and help put them together. The construction of the ISS began in 1998. The first piece was a Russian-built, NASA-funded module called Zarya, which provided the initial power and propulsion. It was launched on a Russian Proton rocket. A few weeks later, the Space Shuttle Endeavour launched, carrying the first American module, a connecting node called Unity. The mission of STS-88 was to rendezvous with the Zarya module and attach Unity to it. This was the very beginning of the station. The crew of Endeavour used the shuttle's robotic arm to grapple the Zarya module and carefully, slowly bring it towards the Unity node, which was held in the payload bay. Then, two spacewalking astronauts, Jerry Ross and James Newman, ventured outside to manually connect the power and data cables between the two modules. With that first, quiet international handshake in orbit, the International Space Station was born. For the next 13 years, this became the primary work of the Space Shuttle program. Mission after mission, the shuttles would launch, carrying another vital piece of the station in their payload bays. One mission would carry up the main American laboratory, the Destiny module. Another would carry up the giant wing-like solar arrays, the station's power source. The solar arrays were so large and so long that they were launched folded up like a complex roadmap and had to be carefully unfurled in space. Other missions would carry up the main truss structure, the long silver backbone of the space station upon which everything else is mounted. And other flights would deliver the connecting nodes, the airlocks, and the European and Japanese laboratory modules. Each of these missions was an incredibly complex and demanding feat of orbital construction, often requiring multiple difficult spacewalks to bolt the new pieces together, to connect the plumbing, and to run the miles of cables.
The Space Shuttle and its crews were, in essence, a high-tech construction crew, building a house in the most extreme environment imaginable. The robotic arm would lift a multi-ton module out of the payload bay with incredible precision. The spacewalking astronauts, floating weightlessly, would then act as orbital ironworkers, using specially designed power tools to bolt the new section into place. It was a slow, meticulous, and incredibly dangerous ballet of humans and machines. Over the course of its construction, there were 37 Space Shuttle flights dedicated to building and servicing the International Space Station. Astronauts conducted over 160 spacewalks from the shuttle and the station to assemble and maintain it. The shuttle was the only vehicle capable of bringing up the large, heavy components. It was also the only vehicle that could bring large crews of up to 7 people, providing the workforce needed for the complex assembly tasks. Without the shuttle and its unique capabilities, the International Space Station as we know it today simply would not exist. It is the shuttle's most visible and most enduring legacy, a gleaming, city-sized outpost that is a permanent symbol of international cooperation, all quietly orbiting 400 kilometers above our heads. It is a house built by a fleet of magnificent, winged, and ultimately transient construction vehicles. And now, we must turn to the darker, more somber chapters of the shuttle's story. For all its triumphs, the incredible complexity of the machine also made it incredibly vulnerable. And twice, in its 30-year history, that vulnerability led to tragedy. This next part of our story is a quiet, respectful reflection on those somber lessons.
In this next part of our quiet journey, we will pause to remember the 2 missions that were lost. It is impossible to tell the full story of the Space Shuttle without acknowledging these moments of tragedy. But our goal here is not to dwell on the horror of the events, but to calmly and respectfully understand what happened and to appreciate the profound and difficult lessons that were learned from them. These are the stories that reshaped NASA's culture and ultimately defined the shuttle's legacy just as much as its triumphs. We begin in January of 1986. The Space Shuttle program was at the height of its confidence. It had flown 24 successful missions.
It seemed to have made spaceflight almost routine. The 25th mission, STS-51L, was special. On board the Space Shuttle Challenger was a high school teacher from New Hampshire named Krista McAuliffe. She was the winner of the Teacher in Space program, a public relations initiative designed to inspire students and to show that spaceflight was becoming accessible to ordinary citizens. The nation was watching with a special sense of excitement and connection. The launch was scheduled for January 28, 1986. The morning was unusually and bitterly cold at the Kennedy Space Center in Florida, with temperatures well below freezing. This cold weather would be the quiet, fatal factor in the disaster that followed. The launch itself looked perfect at first. The shuttle's main engines ignited, followed by the explosive roar of the two solid rocket boosters. Challenger leaped off the launch pad and climbed into the clear blue sky. But just 73 seconds into the flight, as the shuttle was accelerating through the sound barrier, it happened. The entire vehicle was suddenly and catastrophically enveloped in a massive, fiery cloud. The shuttle, with its 7 crew members aboard, was destroyed. The world watched, live on television, in stunned, silent disbelief. The investigation into the Challenger disaster was a long, difficult, and deeply revealing process. A presidential commission, known as the Rogers Commission, was formed to find the cause. And what they found was a story not just of a single technical failure, but of a systemic failure in NASA's own culture. The technical cause was traced back to a specific, seemingly simple component on the right solid rocket booster. The SRBs were built in large segments which were stacked and then sealed together with joints. These joints were sealed by a pair of large rubber rings called O-rings. The job of these O-rings was to contain the incredibly hot, high-pressure gas inside the rocket motor. But the night before the launch had been incredibly cold. The rubber of the O-rings had become stiff and had lost its resiliency. During the launch, as the rocket vibrated and flexed, the cold, stiff O-rings failed to properly seal their joint. A small puff of hot black smoke could be seen coming from the joint at the moment of ignition, a quiet, ominous sign that the seal was not working. For the first minute of flight, the joint seemed to reseal itself. But then, as the shuttle passed through a strong wind shear, the joint flexed again. This time, a flickering flame began to emerge from the faulty seal. This flame acted like a giant blowtorch. It burned through the connecting strut that held the booster to the giant orange external tank. The booster came loose and pivoted, its nose cone striking the top of the external tank. The tank, filled with 500,000 gallons of liquid hydrogen and liquid oxygen, ruptured, and its contents exploded into the massive fireball that was seen on television. The orbiter itself did not explode, but it was torn apart by the immense aerodynamic forces and fell into the Atlantic Ocean.
The investigation into the Challenger disaster went beyond just the technical cause. The Rogers Commission, which included the brilliant physicist Richard Feynman, uncovered a deep and troubling disconnect between NASA's engineers and its management. They found that the engineers at Morton Thiokol, the company that built the SRBs, had known for years that the O-rings were a serious problem and were vulnerable to cold temperatures. On the night before the launch, these engineers had argued passionately against launching in the cold, warning of a potential catastrophe. But their concerns were overridden by managers who were under intense pressure to maintain the shuttle's ambitious launch schedule. Richard Feynman famously demonstrated the O-ring problem in a televised hearing with a simple, brilliant experiment. He took a small piece of the O-ring material, clamped it with a C-clamp, and dipped it into a glass of ice water. When he removed it from the clamp, the normally resilient rubber failed to spring back to its original shape. It remained stiff and flattened. It was a powerful, simple, and undeniable demonstration of the core technical failure. The Challenger disaster was a profound and painful lesson for NASA. It led to a complete redesign of the solid rocket booster joints. But more importantly, it forced a deep, soul-searching review of the agency's safety culture. It showed how a culture of launch pressure and a breakdown in communication could lead to a tragedy. The Space Shuttle program was grounded for nearly 3 years as these technical and cultural problems were addressed. The quiet, tragic lesson of Challenger was that spaceflight could never, ever be considered routine.
Now, let's journey forward in time, 17 years later, to February 1st, 2003. The Space Shuttle program had flown over 80 successful missions since the Challenger disaster. The International Space Station was well under construction. The shuttle was seen as a mature, reliable, and relatively safe vehicle once again. The mission was STS-107, and the orbiter was the very first one ever built, the Columbia. The mission was a 16-day scientific flight, dedicated to experiments in the Space Lab module. It was not an ISS assembly mission, so it didn't have the ability to dock with the station. The launch, on January 16, 2003, appeared to be perfect. Columbia climbed into orbit, and its crew of 7 astronauts began their busy schedule of scientific work. The mission was a great success. But during the launch, something had happened that had gone almost unnoticed. About 82 seconds after liftoff, a piece of insulating foam, about the size of a briefcase, had broken off from the large orange external tank and had struck the leading edge of the orbiter's left wing. Foam strikes were not a new problem. They had happened on many previous shuttle launches, and while NASA engineers were concerned about them, they had come to see them as an acceptable risk, a kind of normal anomaly that had never caused a serious problem before. During the mission, some engineers on the ground did see the foam strike on the launch footage and became concerned. They requested that NASA use spy satellites or other ground-based telescopes to take a closer look at the wing to check for damage. But their requests were denied by management, who felt it was not a serious safety of flight issue. After 16 successful days in orbit, the crew of Columbia prepared to come home. They fired their engines to deorbit and began their long, gliding descent back into the Earth's atmosphere.
The story of the Columbia disaster is a quiet, slow-motion tragedy, the result of a small, seemingly insignificant event that had catastrophic consequences. That piece of foam that had struck the wing was very light, but it was moving at a high relative speed. The impact had punched a hole about the size of a dinner plate in one of the fragile, reinforced carbon-carbon RCC panels on the wing's leading edge. For the entire 16 days of the mission, this hole was a silent, unknown wound on the outside of the orbiter. But as Columbia hit the upper atmosphere during re-entry at over 20 times the speed of light, this small hole became a fatal flaw. The superheated plasma of re-entry, with temperatures of thousands of degrees, began to stream into the interior of the wing through this hole. Inside the wing, this jet of hot plasma began to melt the aluminum structure from the inside out. On the ground, Mission Control began to see strange and puzzling sensor readings from the left wing, but they didn't yet understand the severity of the problem. Inside the cockpit, the crew was likely unaware of the danger until the final moments, as the wing's structure began to fail catastrophically. The loss of the wing caused the orbiter to go into an uncontrollable spin, and the immense aerodynamic forces tore the vehicle apart high over the state of Texas. All 7 astronauts were lost. The investigation that followed was the largest in aviation history. Tens of thousands of volunteers walked through fields and forests, recovering over 84,000 pieces of the orbiter. By reconstructing the debris, investigators were able to pinpoint the exact cause of the disaster. And just as with Challenger, they found that the technical cause, the foam strike, was a symptom of a deeper cultural problem at NASA.
They found that the agency's safety culture had, over time, once again become complacent, normalizing a known and dangerous flaw.
The Columbia disaster was another profound and painful lesson. It showed, once again, the incredible complexity and inherent danger of the Space Shuttle system. The shuttle was an amazing machine, but it was, as the investigation board concluded, an unforgiving one. There was very little margin for error. The disaster led to another long 2.5-year grounding of the shuttle fleet as NASA worked to understand and mitigate the foam shedding problem. But it also led to a much bigger and more fundamental decision. It was now clear that the aging shuttle fleet, for all its amazing capabilities, would never be a truly safe or routine way to get to space. The decision was made to use the remaining shuttle flights only to complete the assembly of the International Space Station and then to retire the program for good. The quiet, tragic lesson of Columbia was the final chapter in the story of the Space Shuttle's operational life. This brings us to the final part of our story tonight, the end of an era and the quiet retirement of these magnificent, flawed machines. For the first time, the shuttle was equipped with a long 50-foot robotic arm extension with a high-resolution camera on the end. A key part of every mission from now on would be a long, slow, and meticulous inspection of the entire orbiter's heat shield while in orbit. The crew would use the robotic arm to scan every inch of the tiles and the wing edges, and the images would be sent down to a team of hundreds of engineers on the ground who would look for any sign of damage.
The centerpiece of this new safety philosophy was a 50-foot-long extension for the shuttle's robotic arm, known as the Orbiter Boom Sensor System, or OBSS. It was essentially a long pole with a sophisticated package of cameras and lasers on the end. On the second day of every mission following the Columbia disaster, the crew would use the main Canadarm to lift this long boom out of the payload bay. Then, for the next several hours, they would undertake a slow, meticulous, and almost meditative process of scanning the entire spacecraft. They would carefully guide the boom's camera package over every inch of the orbiter's fragile heat shield, the wing's leading edges, the nose cone, and the thousands of tiles on its belly. The high-resolution images and laser data would be beamed down to a dedicated team of hundreds of engineers on the ground at the Johnson Space Center. This team would work around the clock, poring over every image, looking for any sign of damage, any chip or crack in the tiles or the carbon panels that might pose a threat during re-entry. It was a quiet, painstaking, and incredibly high-stakes inspection. This new procedure also led to another major change in mission planning. The International Space Station, which the shuttle had spent a decade building, now took on a new and critical role. It was a safe haven. Every shuttle mission from then on was planned so that if any potentially mission-ending damage was found on the orbiter, the crew could fly to the ISS and dock. They could then wait there, living on the station, while NASA launched a rescue shuttle to bring them home. This rescue mission was always on standby, ready to be launched within a few weeks. Thankfully, a full rescue was never needed, but the ISS provided a crucial psychological and physical safety net that had never existed before. The return to flight missions also saw the development of another incredible, though thankfully never used, capability: in-flight heat shield repair. NASA engineers developed a whole new set of tools and techniques for astronauts to perform spacewalks to fix potential damage to the orbiter's tiles or carbon panels. They had special caulking gun-like tools that could extrude a heat-resistant material to fill in cracks. They developed small, thin plates that could be bolted over a larger hole to protect the structure underneath. The astronauts trained for these complex repair scenarios for hundreds of hours in the giant water tanks at the Neutral Buoyancy Laboratory in Houston. It was an incredible feat of engineering and planning, figuring out how a person in a bulky, pressurized spacesuit could perform such a delicate and precise repair job while floating in the vacuum of space. The fact that these procedures were developed and ready to be used is a testament to the lessons learned from the Columbia tragedy. The era of accepting small, seemingly insignificant risks was over. The final years of the shuttle program were defined by a culture of deep, quiet, and meticulous vigilance. And so, with these new safety measures in place, the Space Shuttle fleet embarked on its final chapter. The decision had been made to retire the orbiters once the primary construction of the International Space Station was complete. The final missions were imbued with a powerful sense of history, a feeling of a great era coming to a quiet close. Let's take a slow walk through the final voyages of these magnificent winged spaceships. The first of the orbiters to make its final flight was Discovery, on mission STS-133 in early 2011. Discovery was the workhorse of the fleet, having flown more missions than any other orbiter. It was a true veteran of the program. Its final mission was a fitting one. It delivered a new permanent module, the Leonardo Permanent Multi-Purpose Module, to the International Space Station, providing much-needed storage space.
The mission was a great success. The crew of Discovery performed 2 spacewalks and helped to install the new module. But the entire flight was overlaid with a sense of poignant finality. The astronauts took time to appreciate the view, to soak in the experience of living and working on this historic vehicle for the last time. When Discovery undocked from the ISS for the final time, the station crew rang the ship's bell, a naval tradition, and said, "Discovery, departing." The pilot of the shuttle then flew a slow, graceful victory lap around the station, a final, beautiful orbital salute between the 2 incredible structures whose histories were so deeply intertwined. When Discovery landed for the final time at the Kennedy Space Center on March 9, 2011, it was a moment of quiet celebration and deep nostalgia. It had successfully completed 39 missions, spent over a full year in space, and had carried more astronauts than any other single spacecraft in history. It had launched the Hubble Space Telescope. It had been the first shuttle to dock with the Mir space station. Its long and storied career was now over. The first of the great birds was now safely in the nest, forever. Just a couple of months later, in May of 2011, it was Endeavour's turn. The final mission of Endeavour, STS-134, was one of the most scientifically important of the entire program. Its primary payload was the Alpha Magnetic Spectrometer, a massive 7.5-ton particle physics experiment that would be attached to the outside of the space station to search for evidence of dark matter and antimatter. Endeavour itself has a special history. It was the youngest of the orbiters, the one built in the early 1990s to replace the Space Shuttle Challenger. It was, in many ways, the most advanced of the fleet, incorporating many of the safety upgrades and technological improvements that had been developed after the Challenger disaster. And its most famous mission, of course, was its very first long flight, the historic mission to repair the Hubble Space Telescope. It was a vehicle born from tragedy, and it went on to perform some of the program's greatest triumphs.
The final mission of Endeavour was another resounding success. The crew, commanded by Mark Kelly, successfully installed the Alpha Magnetic Spectrometer onto the station's truss in a series of complex spacewalks. It was one of the last major pieces of construction for the U.S. segment of the ISS. And then, after a final farewell, Endeavour 2 undocked from the station for the last time and began its journey home. It landed smoothly at the Kennedy Space Center on June 1, 2011. Another chapter had closed. And that left only one. The final mission of the entire Space Shuttle program was STS-135, flown by the orbiter Atlantis in July of 2011. This mission was a strange and special one. It had originally been planned only as a launch-on-need rescue mission for the Endeavour flight.
But NASA decided to go ahead and fly it as a full-fledged mission to deliver one last load of vital supplies and spare parts to the International Space Station. Because it was added to the schedule so late, it was a lean mission. Instead of the usual crew of 6 or 7, Atlantis flew with a smaller crew of just 4 experienced astronauts. This was a safety precaution. In the unlikely event that Atlantis was also damaged during launch, there would be no shuttle left on Earth to come and rescue them. The plan in this emergency scenario was for the 4 astronauts to stay on the ISS and return to Earth one by one over the course of a year in Russian Soyuz capsules. It was a quiet, sobering reminder that even on this final triumphant flight, the risks were still very real. The launch of Atlantis was a huge public event. Hundreds of thousands of people flocked to Florida to witness the end of an era, the very last time one of these magnificent white birds would climb to orbit. The mission itself was a flawless success. They delivered their cargo, spent a quiet and historic week docked with the space station, and then they too undocked for the final time.
The final landing of Atlantis on July 21, 2011 was a moment of profound historical weight. It happened in the pre-dawn darkness at the Kennedy Space Center. As the orbiter descended, its twin sonic booms echoed across the Florida coast for the last time. It then emerged from the darkness, a beautiful, silent glider, and touched down perfectly on the runway. As it rolled to a stop, the mission commander, Chris Ferguson, made a final, poignant radio call. "Mission complete, Houston." After serving the world for over 30 years, the Space Shuttle has earned its place in history, and it's come to a final stop. In mission control, there was quiet, respectful applause. The 30-year story of the Space Shuttle, a story of incredible triumphs and deep tragedies, of brilliant engineering and quiet courage, was over. But the story of the orbiters themselves was not quite finished. The question now was, what do you do with a used spaceship? These were not just machines, they were historical artifacts of immense significance. And so began the final slow and sometimes strange process of decommissioning them. After Atlantis landed, it and its sister ships, Discovery and Endeavour, had to be made safe for public display. This was a complex and meticulous process. The pods containing the powerful and toxic hypergolic rocket propellants for the maneuvering thrusters had to be carefully drained and purged. The main engines were removed as they were to be potentially reused for future rocket programs, and all the hazardous materials had to be carefully removed. It was a quiet reverse assembly line, slowly transforming a complex flying machine into a safe, inert museum piece. And then came the final journeys. How do you get a 100-ton spaceship to a museum in another city? For 2 of the orbiters, the answer was the same way they had always been transported, on the back of a specially modified Boeing 747 called the Shuttle Carrier Aircraft.
Let's now take a final, quiet tour of the final resting places of these magnificent machines. It is a journey to 4 different cities across America, where you can still go today and stand in the presence of these historic vehicles. Our first stop is in the Washington, D.C. area, at the Smithsonian's National Air and Space Museum's Stephen F. Udvar-Hazy Center. This is the home of the orbiter Discovery. In April of 2012, Discovery was loaded onto the back of the 747 shuttle carrier aircraft for its final flight. It took off from the Kennedy Space Center and performed a spectacular low-altitude farewell tour over Washington, D.C., flying past the monuments and landmarks before landing at Dulles International Airport. It now sits as the centerpiece of the museum's space hangar, and to see it in person is a truly humbling experience. The first thing that strikes you is its sheer size. On television, it looks graceful and almost small. In person, it is a behemoth. You can walk right underneath its delta wing,
You can see the thousands of individual heat shield tiles, each one with a unique serial number. And you can see the subtle scorch marks and battle scars from its 39 fiery re-entries into the Earth's atmosphere. It is not a pristine model, it is a veteran, a machine that has truly been to space and back, again and again. It is a quiet, powerful, and deeply impressive sight. Next on our tour, we visit the orbiter that was built to replace the Challenger. We go to the California Science Center in Los Angeles, the home of Endeavour. Endeavour's final journey in 2012 was perhaps the most spectacular of all. After flying cross-country on the back of the 747, it landed at Los Angeles International Airport. But the Science Center is many miles from the airport.
So for its final journey, Endeavour was carefully loaded onto a massive, multi-wheeled land transporter. And then for 2 days, it was slowly, painstakingly driven through the streets of Los Angeles and Inglewood. It was a surreal and beautiful parade. The giant white winged spaceship crawled past suburban houses, fast food restaurants, and convenience stores. People lined the streets, cheering and taking pictures. Trees had to be trimmed, and power lines had to be temporarily moved to make way for the orbiter's giant wingspan. It was a strange, slow, and wonderfully public final mission, a spaceship causing a traffic jam on its way to its new home. Endeavour is currently on display in a temporary hangar, but the Science Center is building a magnificent new museum, the Samuel Ocean Air and Space Center, which will display Endeavour in a truly unique way. It will be the only place in the world where a real space shuttle will be displayed vertically, in a full stack configuration, attached to a real but inert orange external tank and 2 solid rocket boosters. It will look exactly as it did on the launch pad, a colossal 200-foot-tall monument to the power and ambition of the shuttle era. Our third stop takes us back to Florida, to the Kennedy Space Center Visitor Complex. This is the home of the final orbiter to fly, Atlantis. Atlantis didn't have to fly on a 747. It was simply towed a few miles from the orbiter processing facility to its magnificent new custom-built exhibition hall. The exhibit for Atlantis is one of the most dramatic museum displays ever created. When you first walk in, you watch a film about the shuttle program. At its conclusion, the screen rises and you are met with a breathtaking sight. The orbiter Atlantis is suspended in front of you, seemingly floating in space. It is tilted at a precise 43.21-degree angle, with its payload bay doors wide open and its robotic Canadarm extended, as if it is still performing a mission in orbit. You can walk underneath it and look up into the complex payload bay. It is a stunning, beautiful, and deeply moving display that perfectly captures the grace and the complexity of the machine in its natural, weightless environment.
Our final stop on this tour is in New York City, at the Intrepid Sea, Air, and Space Museum, which is housed on a historic aircraft carrier docked on the Hudson River. Here, inside its own special pavilion, you will find the original prototype orbiter, the Enterprise. The Enterprise has its own unique and important story. It was the very first orbiter ever built, completed in 1976. It was originally going to be named Constitution, but a massive letter-writing campaign by fans of the TV show Star Trek convinced President Gerald Ford to name it after the famous starship from the show. The Enterprise was not a full-fledged spaceship. It had no main engines and no functional heat shield. Its purpose was to be a test vehicle, to prove that a 100-ton winged brick could actually fly like a glider. In 1977, it was carried to high altitude by the 747 shuttle carrier aircraft and then released. Astronaut crews then piloted the Enterprise through a series of steep gliding descents to perfect landings on a dry lake bed in California. These approach and landing tests were a crucial part of the program, proving that the shuttle could land safely before they ever attempted it from orbit.
After its test program was over, the Enterprise was used for ground-based fit checks and was eventually retired to the Smithsonian. It is a quiet but essential part of the shuttle's history, the one that paved the way for all the others. Seeing these four magnificent machines, these quiet giants resting in their halls, is a powerful and poignant experience. They are the tangible physical legacy of a 30-year-long chapter in our human journey into the cosmos.
And so we have come to the end of our long, slow, and quiet story of the Space Shuttle. We have journeyed from the ambitious dreams of the 1960s to the somber realities of its retirement. We have explored the incredible complex machine itself, from its powerful engines to its fragile tiled skin. We have lived a week in orbit, understanding the daily routines of the astronauts who called it home. We have celebrated its greatest triumphs, the missions that saved the Hubble telescope and built the International Space Station. And we have quietly and respectfully reflected on its two great tragedies and the painful but vital lessons they taught us. What then is the final legacy of this incredible vehicle? It is a complex and a mixed one. The shuttle was born from a dream of making spaceflight routine and affordable, and in that, it ultimately failed. The incredible complexity of the vehicle meant that it never flew as often as planned. The turnaround time between missions was months, not weeks, and the cost per flight remained astronomically high. It was not the cheap, reliable space truck that NASA had promised. It was also a machine that was born from compromise, and those compromises, particularly the solid rocket boosters and the fragile heat shield tiles, made it an inherently more dangerous vehicle than the simple capsules that had come before. The loss of two orbiters and their crews is a permanent and tragic part of its story. But for all its flaws, the Space Shuttle was also a machine of breathtaking beauty and incredible capability. Its ability to carry large cargo, to have a robotic arm, and to bring satellites and equipment back to Earth was unique in the world. It was a remarkable, one-of-a-kind vehicle that allowed us to do things in space that would have been otherwise impossible. We've talked about the importance of a functional toilet in space and the quiet heroism of the ISS's modern system. The Space Shuttle's toilet, officially known as the Waste Collection System, or WCS, was an earlier and much more temperamental piece of engineering. It was a hybrid system, trying to improve upon the horrors of the Apollo bags while still being compact enough to fit into the tiny bathroom area on the shuttle's middeck, and it was, by all accounts, an adventure to use. Like all space toilets, it used airflow instead of water to direct the waste. But its design had a few unique and rather infamous features. For solid waste, it didn't use a simple bag system. It had a small, round opening, much smaller than a toilet on Earth, and beneath it was a cylindrical container. To ensure the waste didn't just pile up at the opening, the system featured a rotating fan-like device at the bottom of the container called a slinger. When activated, this slinger would spin at high speed, flinging the solid waste against the walls of the collection container, where it would slowly be dried out by exposure to the vacuum of space. This system was mechanically complex, and it was prone to failure. The astronauts' memoirs are filled with darkly humorous stories of having to perform in-flight repairs on the slinger motor or other parts of the toilet. It was a task that required a strong stomach and a good sense of humor. The urine collection system was a separate hose with a funnel, similar to the one on the ISS, which used airflow to pull the liquid into a storage tank. This wastewater wasn't recycled on the shuttle, it was simply vented into space at regular intervals. The urine would instantly freeze into a cloud of tiny, glittering ice crystals, creating a beautiful, if slightly strange, private meteor shower for the shuttle on its journey.
Using the shuttle's toilet required a level of skill and precision that is hard to imagine. The opening for solid waste was only about 4 inches in diameter,
To use it correctly, an astronaut had to position themselves perfectly over this tiny opening to create a good seal, using special thigh restraints and handholds to keep themselves from floating away. To help with this, NASA created a special positional trainer on the ground, which was an exact replica of the shuttle toilet, but with a camera installed inside the bowl. Astronauts would have to spend time on this trainer, watching themselves on a monitor to learn the exact body position needed to ensure a successful use event, as it was clinically called. It was often cited as one of the most awkward and humbling parts of astronaut training. Even with all this training, things could still go wrong. The system had a tendency to get clogged, and the fans could fail. And because the shuttle was a reusable vehicle, any messes that were made had to be thoroughly cleaned up by the crew before landing. The quiet, unglamorous job of cleaning the bathroom became one of the most important end-of-mission tasks. The shuttle toilet is a perfect example of the immense, hidden challenges of human spaceflight. It's a quiet reminder that for every glorious spacewalk and every stunning view of the Earth, there were dozens of small, difficult, and sometimes deeply unpleasant tasks that had to be performed just to make daily life possible. The astronauts who flew the shuttle were not just brilliant pilots and scientists, they were also incredibly patient and resilient plumbers, mechanics, and housekeepers. Their ability to handle these challenges with professionalism and good humor is a quiet testament to their fortitude. Now, from one of the least glamorous pieces of hardware, let's turn to one of the most elegant and iconic. Let's take a deeper look at the Canadarm.
The official name for the arm was the Shuttle Remote Manipulator System, or SRMS, but it quickly became known around the world by its affectionate nickname. It was a source of immense national pride for Canada, whose engineers at a company called Spar Aerospace designed and built it. It was one of the most successful and reliable pieces of technology in the entire Space Shuttle program. The Canadarm was a robotic arm of incredible dexterity. It was about 15 meters, or 50 feet, long and had a diameter of only about 38 centimeters. It was designed to be incredibly lightweight, weighing only about 410 kilograms on Earth, but it was strong enough to move massive payloads weighing tens of thousands of kilograms in the weightless environment of space. Its design was modeled on the human arm. It had joints that mimicked a shoulder, an elbow, and a wrist, giving it 6 degrees of freedom of movement. This meant it could move in any direction and orient itself at any angle. At the end of the arm was the end effector. This was the shuttle's hand. It was not a grasping claw, but a clever cylindrical device containing a system of 3 snare wires. To capture a satellite, the astronaut controlling the arm would gently fly this end effector over a special grapple fixture on the satellite. They would then trigger the snare wires, which would close around the grapple fixture, creating a strong, stable connection. The entire arm was controlled by an astronaut sitting at the aft flight deck of the shuttle, looking out the back windows into the payload bay. They used a set of 2 joysticks and a series of switches to control the arm's movement with incredible precision. It was a task that required immense concentration and a very good sense of 3-dimensional space. The arm moved very slowly and deliberately to avoid any sudden movements that could damage the shuttle or the payload.
The first flight of the Canadarm was on the second Space Shuttle mission, STS-2, aboard Columbia in 1981. The astronauts, Joe Engle and Richard Truly, put the new arm through its paces, moving it through all its different positions. They famously had a bit of trouble at first, as the instruction manual had some pages printed in the wrong order, a quiet, very human problem on a high-tech mission. But they quickly figured it out. On a later mission, they even used the arm to hold up a small sign that said, "Go Leafs Go," for the television cameras, a friendly nod to their Canadian partners. Over its 30-year career, the Canadarm became an indispensable tool.
It deployed famous spacecraft like the Hubble Space Telescope and the Galileo probe to Jupiter. It retrieved malfunctioning satellites like SolarMax and Westar 6, bringing them into the payload bay for daring spacewalking repairs. And, as we've discussed, it was the primary construction tool for the International Space Station, lifting giant truss segments and entire laboratory modules out of the shuttle's bay and carefully putting them into place. The Canadarm was so successful that it spawned an entire family of space robotics. The larger Canadarm2 is now a permanent fixture on the International Space Station, and a smaller, more nimble robotic arm called Dextre acts as the station's handyman. The legacy of the original shuttle arm is one of quiet, reliable, and elegant precision. It was the gentle giant that built our home in orbit, a beautiful example of international cooperation, and a testament to the idea that sometimes the most powerful tool in space is not a rocket engine, but a long, graceful, and very clever arm. Now, let's turn our attention back to the orbiter's skin and take a deeper look at the quiet, painstaking world of the thermal protection system, the heat shield tiles.
We know that the shuttle was covered in over 24,000 of these individual silica tiles, but the sheer complexity of this system is worth dwelling on. Each tile was a unique, precisely machined and shaped piece of a colossal, three-dimensional jigsaw puzzle. The reason for this was that the orbiter's skin was not a simple shape. It was a complex series of curves and angles, and each tile had to be perfectly fitted to its specific location. The manufacturing process for each tile was incredibly complex. They were made from a slurry of pure silica fibers derived from high-quality sand. This slurry was mixed with water and other chemicals and then poured into molds. After being dried, the resulting block of lightweight, porous material was then fired in a giant kiln, much like pottery. The result was a tile that was about 90% empty space by volume, a kind of ceramic styrofoam. This is what gave them their incredible insulating properties. After being fired, each tile had to be machined with incredible precision to its exact, unique shape. Then, most of the tiles were coated with a special black glassy coating, which was designed to have a very high emissivity. This meant it was very good at radiating heat away into space, which helped to keep the orbiter cool. The white tiles on the top surfaces of the shuttle had a different coating, designed to reflect the heat of the sun while in orbit. The process of attaching these tiles to the shuttle's aluminum frame was another huge challenge. You couldn't just glue them on directly. The aluminum frame would flex and bend from the stresses of launch and landing, and the brittle ceramic tiles would crack. So each tile was first glued to a soft, flexible felt pad called a strain isolator pad, and then this pad was glued to the shuttle. This soft layer would absorb the flexing of the frame and protect the tile. The entire process of manufacturing, coating, and installing these thousands of individual tiles was one of the most labor-intensive and expensive parts of the entire Space Shuttle program.
After every single flight, the orbiter would be towed back to the orbiter processing facility, and a team of hundreds of technicians would begin a long and painstaking inspection of every single one of those 24,000 tiles. They would examine each tile for chips, cracks, or any sign of damage from the previous mission. Any damaged tile had to be carefully removed and replaced. This was a delicate and time-consuming process, and it created a huge logistical challenge. NASA had to maintain a massive inventory of thousands of spare tiles, each one with its own unique computer-milled shape ready to replace a damaged one. This long and expensive turnaround time for tile inspection and repair was one of the key reasons why the shuttle could never fly as frequently as it was originally intended to. After the Columbia disaster, which was caused by damage to the heat shield, this inspection process became even more rigorous. And NASA also developed a series of ingenious, if slightly desperate-sounding kits for astronauts to repair a damaged tile in orbit.
One of the main tools was a device that looked a bit like a futuristic caulking gun. It was nicknamed the goo gun. It was filled with a special, heat-resistant black, gooey material called NOAX. If a small crack or gouge was found on a tile, a spacewalking astronaut could use this gun to extrude a ribbon of the NOAX material into the damaged area to fill it. For larger damage, they developed a kind of plug. This was a thin, flexible plate made of a carbon-silicon composite that could be bolted over a damaged area of the heat shield to protect it. The astronauts trained for hundreds of hours in the underwater neutral buoyancy lab, practicing these delicate repair techniques. Thankfully, they never had to use them on a real mission. But the quiet, incredible fact that we had developed the ability for a human being in a bulky spacesuit to perform open-heart surgery on the skin of a spaceship while flying at 28,000 kilometers per hour is a testament to the lessons learned from tragedy.
Now that we have explored the shuttle's systems in such detail, let's return to its greatest triumph, the mission that defined its legacy. Let's take a quieter, more detailed look at the story of saving Hubble. The discovery of the flaw in Hubble's mirror was one of the most devastating moments in the history of modern astronomy. The telescope had been decades in the making. It was the most expensive scientific instrument ever built, and its primary mirror, the very heart of the telescope, had been ground to the wrong shape. The error was almost impossibly small. The edge of the mirror was too flat by just 2 microns, about 1/50th the thickness of a human hair. But in the precise world of optics, this tiny error was catastrophic. It caused a fuzzy halo of light around every star, a problem called spherical aberration, which made it impossible to see the faint, distant objects that Hubble was built to discover. The public outcry was immense. The telescope was called a billion-dollar blunder. But the quiet genius of Hubble's design was that it was always intended to be serviced in orbit by the Space Shuttle. So while the scientists and the public despaired, the engineers at NASA got to work on a solution. The plan they devised was brilliant. It was to install a new instrument inside the telescope called CoStar. CoStar was not a camera. It was essentially a robotic arm with a series of 5 pairs of tiny corrective mirrors. These mirrors were shaped with a flaw that was the exact opposite of the flaw in the main mirror. The idea was that the CoStar mirrors would intercept the blurry light from the main mirror, correct its path, and then feed that now perfectly focused light to the other scientific instruments. It was, quite literally, a pair of eyeglasses for a giant telescope. In addition, they would replace the main camera with a new one that had its own built-in corrective optics. It was an incredibly delicate and complex plan, and its success would depend entirely on the skill of a team of spacewalking astronauts.
The mission to save Hubble, STS-61, aboard the shuttle Endeavour in December of 1993, was one of the most ambitious and demanding flights ever attempted. It was planned to involve a record-breaking 5 consecutive spacewalks. The crew was a team of veteran astronauts, including the highly experienced Story Musgrave, who was on his 5th spaceflight. The first task was to capture the giant school bus-sized telescope. This was a delicate orbital dance. The shuttle had to approach Hubble very carefully to avoid contaminating its optics with thruster firings. Then the Canadarm, operated with millimeter precision, reached out and grappled the telescope, pulling it gently into the payload bay where it could be anchored for the repairs. The 5 spacewalks that followed were a long and grueling marathon of quiet, focused, and incredibly difficult work. Nothing about it was easy. The astronauts were working in the deep cold of space, where temperatures could swing by hundreds of degrees. The bolts on the old instruments were frozen and difficult to turn. The access panels were stiff and hard to open. One of the most dramatic moments came when they were trying to replace the telescope's giant wing-like solar arrays. One of the arrays had warped in the temperature extremes and would not retract properly. For long, tense minutes, spacewalkers Story Musgrave and Jeffrey Hoffman had to struggle with the giant, unwieldy structure, eventually having to jettison it manually. On another spacewalk, they had to install the new wide-field planetary camera, a device the size of a baby grand piano, into a narrow slot inside the telescope, with only inches of clearance on either side. It was like trying to slide a refrigerator into a tight kitchen alcove, but while wearing the world's stiffest, bulkiest winter clothes, and while floating in zero gravity.
Each of the 5 spacewalks lasted for over 7 hours. The work was physically and mentally exhausting. The astronauts had to rely on their years of training in the giant water tank back on Earth, where they had practiced every single step of their tasks over and over again. The success of the mission was a testament to the power of that quiet, repetitive, and meticulous preparation. Finally, after 5 long days of this intense orbital surgery, the work was done. The new camera was in. The CoStar corrective optics were installed. The new solar panels were deployed. It was time to release the telescope back into the wild. With incredible gentleness, the Canadarm lifted the newly refurbished Hubble out of the payload bay and released it back into its own orbit. The crew of Endeavour then flew a slow, careful departure. Their job was over. Now the entire world had to wait for several anxious weeks while the scientists on the ground powered up the new instruments and took the first new pictures. On Christmas Eve of 1993, the first images from the repaired Hubble were released to the public, and they were breathtaking. The blurry, disappointing halos were gone. In their place were razor-sharp, crystal-clear images of distant stars and galaxies. A picture of the spiral galaxy M100, which had once been a fuzzy blob, was now a stunning, intricate masterpiece, with individual stars visible in its spiral arms. The repair had worked. It had worked perfectly. The Hubble repair mission was the shuttle's redemption. It transformed what could have been NASA's greatest failure into its finest hour. It showcased the shuttle's unique ability to be not just a delivery truck, but a workshop, a garage, and a hospital for our most precious scientific instruments. It was a quiet, beautiful, and deeply inspiring story of human ingenuity and perseverance.
Now let's spend a little more quiet time on the shuttle's other great construction project, the International Space Station. We know the shuttle was the workhorse that built the station, but let's appreciate the scale of that work. The ISS is the largest and most complex structure ever built in space. Its main truss, the long backbone that holds the giant solar arrays, is longer than an American football field. The station has a mass of nearly 1 million pounds, and almost all of that was delivered, piece by massive piece, by the Space Shuttle. Let's think about a typical assembly mission. A mission like STS-110, flown by Atlantis in 2002, had the primary task of delivering the S0 truss segment. This was the central, cornerstone piece of the station's entire truss structure. It was a 13-ton, 44-foot-long piece of complex aluminum framework. The mission to install it was a quiet symphony of robotics and human spacewalking. First, the crew used the shuttle's Canadarm to lift the massive S0 truss out of the payload bay. Then, they handed it off to the station's own robotic arm, the Canadarm 2, which was already in place. The Canadarm 2 would then hold the truss segment in position while 2 spacewalking astronauts, Steve Smith and Rex Walheim, went to work. For hours, they floated around the massive structure, using specially designed power tools that looked like futuristic drills to bolt the new truss segment into place. They had to connect dozens of power, data, and fluid cables, a task made incredibly difficult by their bulky, pressurized gloves. At the end of their spacewalk, they used the station's new mobile transporter, a kind of railway car that rides along the truss, to move themselves and their equipment into position for the next day's work. The entire mission was a quiet, complex and perfectly executed piece of high-altitude construction work. And this same basic story was repeated with different modules and different crews for over a decade.
And now we must navigate our quiet journey into a more somber and difficult part of the Space Shuttle's story. For all its incredible triumphs, for all its beauty and its grace, the shuttle was an experimental vehicle, pushing the boundaries of technology with every single flight. Its immense complexity also made it incredibly vulnerable. And twice in its 30-year career, that inherent risk became a tragic reality. It is impossible to tell the full story of the shuttle without acknowledging these moments of loss. But our goal here is not to dwell on the horror or the heartbreak of the events themselves. Instead, we will do what the engineers and scientists at NASA had to do. We will calmly and respectfully try to understand what happened, and to appreciate the profound and difficult lessons that were learned from these tragedies. These are the stories that reshaped NASA's culture, that redefined our understanding of risk, and that ultimately determined the fate of the entire Space Shuttle program. They are the somber, quiet, and essential chapters in the life of this magnificent machine. We begin in January of 1986. The Space Shuttle program was at the absolute height of its public confidence and popularity. It had flown 24 successful missions back-to-back. It seemed to have made the incredible feat of spaceflight feel almost routine, almost easy. The 25th mission, STS-51L, was set to be a special one. This was the flight that would carry the Teacher in Space, a high school social studies teacher from New Hampshire named Krista McAuliffe. She had been selected from thousands of applicants to be the first ordinary citizen to fly in space. Her presence on the crew had captured the imagination of the entire country. School children across America were going to watch the launch live in their classrooms. There was a palpable sense of excitement and a deep personal connection to this particular mission.
The launch of the Space Shuttle Challenger was scheduled for the morning of January 28, 1986. The weather at the Kennedy Space Center in Florida was unusual. A cold front had moved through, and the temperatures overnight had dropped well below freezing. There were long, beautiful icicles hanging from the launch tower. This bitter, un-Floridian cold would become the single most critical factor in the events that followed. Despite the cold, the countdown proceeded. At 11:38 a.m., the shuttle's main engines ignited, followed by the deep, explosive roar of the two solid rocket boosters. The Challenger leaped off the launch pad and began its powerful ascent into a clear blue sky. For the first minute, the launch looked completely normal, completely perfect. But the technical story of the disaster had actually begun in the very first second of the flight. The intense cold had caused the rubber O-rings, which were meant to seal the joints between the segments of the right solid rocket booster, to become stiff and lose their resiliency. As the rocket ignited and flexed, these cold, stiff O-rings failed to create a proper seal. A tiny puff of hot, black smoke could be seen coming from a joint on the booster at the moment of ignition. It was a quiet, ominous, and tragically missed signal that the seal was not working. For the first minute, the joint seemed to reseal itself, plugged by the rocket's own solid fuel. But then, as the shuttle passed through a strong patch of wind shear high in the atmosphere, the rocket flexed again. This time, the plug was dislodged, and a small, flickering flame emerged from the faulty joint. This flame acted like a giant, high-pressure blowtorch. It grew larger and began to burn through the connecting strut that held the bottom of the booster to the giant orange external tank. At 73 seconds into the flight, the strut gave way. The booster came loose and pivoted, its nose cone striking the top of the external tank. The tank, filled with over 500,000 gallons of liquid hydrogen and liquid oxygen, ruptured. The two propellants mixed and ignited, and the entire vehicle was instantly enveloped in a massive, fiery cloud. The orbiter itself, traveling at nearly twice the speed of light, was torn apart by the immense aerodynamic forces. The 7 members of the Challenger crew were lost.
The Challenger disaster was a moment of profound national trauma. The investigation that followed, led by a presidential commission known as the Rogers Commission, was a long, difficult, and deeply revealing process. Its goal was not just to find the technical cause, but to understand the organizational failures that had allowed it to happen. The technical cause, the failure of the O-ring seal in the cold weather, was quickly identified, but the Commission's deeper investigation, famously spearheaded by the brilliant and fiercely independent physicist Richard Feynman, uncovered a troubling reality within NASA's culture at the time. They discovered that the engineers at Morton Thiokol, the company that built the solid rocket boosters, had known for years that the O-rings were a potential problem. They had seen evidence of partial O-ring erosion on previous flights, and they knew that the rubber was not certified to perform correctly at low temperatures. On the night before the launch, these engineers had argued passionately for hours with NASA management, warning them that launching in the unprecedented cold was a terrible risk. They had presented data and strongly recommended that the launch be postponed. But their concerns were overridden by NASA managers who were under intense pressure to maintain the shuttle's ambitious and politically important launch schedule. The managers, who were less familiar with the technical details, made a fatal decision based on incomplete information and external pressures. Richard Feynman famously and dramatically demonstrated the core technical problem during a televised public hearing. He got a small sample of the O-ring material, clamped it with a C-clamp to simulate the pressure of the joint, and then dipped it into a simple glass of ice water. When he removed the material from the clamp, the normally resilient rubber failed to spring back to its original shape. It remained stiff and flattened. "I believe," he said quietly, "that has some significance for our problem." It was a powerful, simple, and undeniable demonstration of the reason for the disaster.
The Challenger disaster was a profound and painful lesson for NASA and for the entire country. It was a story not just of a failed piece of rubber, but of a failure in communication, a failure of management, and a failure of what investigators called NASA's safety culture. The agency had become so accustomed to success that it had begun to accept known risks as normal and acceptable. The aftermath led to a complete redesign of the solid rocket booster joints, with a new 3-ring seal and built-in heaters. But more importantly, it forced a deep, soul-searching review of the agency's entire decision-making process. The Space Shuttle program was grounded for nearly 3 years, a long and quiet pause as these technical and deep cultural problems were addressed. The quiet, tragic lesson of Challenger was a reminder that spaceflight is never routine and that the voices of concerned engineers must always be heard. Now, let's journey forward in time, 17 years later, to the first day of February 2003. The Space Shuttle program had flown over 80 successful missions since the Challenger disaster. A new culture of safety was in place. The construction of the International Space Station was well underway. The shuttle was once again seen as a mature, reliable, and relatively safe vehicle. The mission was STS-107, and the orbiter was the very first one ever built, the grand old lady of the fleet, Columbia. The mission was a 16-day scientific flight dedicated to a host of experiments in the Space Lab module. Because it was a science mission to a different orbit, it did not have the ability to dock with the International Space Station. This would prove to be a critical and fatal fact. The launch on January 16, 2003, appeared to be completely perfect. Columbia climbed into orbit without any obvious issues, and its crew of 7 astronauts, including the first Israeli astronaut, Ilan Ramon, began their busy schedule of round-the-clock scientific work. The mission was, by all accounts, a great success. But during the launch, something had happened that had been seen before, but whose consequences were not fully understood. About 82 seconds after liftoff, a piece of insulating foam, about the size of a briefcase, had broken off from the large orange external tank and had struck the leading edge of the orbiter's left wing.
The story of the Columbia disaster is a quiet, slow-motion tragedy, the result of a small, seemingly insignificant event that had catastrophic consequences that would only be revealed at the very end of the mission. Foam strikes, like the one that hit Columbia, were not a new problem. They had happened to varying degrees on many previous shuttle launches. The insulating foam on the external tank was known to sometimes break away during the intense vibrations of ascent. And while NASA engineers were concerned about it, these foam strikes had come to be seen as an acceptable risk, a kind of normal anomaly that had never caused a catastrophic failure before. It was seen as a maintenance issue, a problem that could damage the fragile heat shield tiles, but not a fundamental threat to the safety of the orbiter itself. This gradual acceptance of a known flaw was a quiet and dangerous echo of the cultural problems that had led to the Challenger disaster. It was a phenomenon the investigation board would later call the normalization of deviance. During the 16-day mission, a team of engineers on the ground did see the foam strike on a detailed review of the launch footage. They became very concerned about the potential for damage to the wing. They requested, multiple times, that NASA use spy satellites or other powerful ground-based telescopes to take a closer look at the wing while the shuttle was in orbit to check for any damage. But their requests were ultimately denied by mid-level NASA management, who felt that the foam strike was a known and acceptable risk, and that even if damage was found, there was little the astronauts could do to fix it. This was another critical and tragic miscalculation. So for 16 days, the crew of Columbia orbited the Earth, completely unaware of the mortal wound that their spaceship had sustained. They completed their scientific mission with great success. And then, on the morning of February 1st, 2003, they prepared to come home. They fired their engines to deorbit and began their long, gliding descent back into the Earth's atmosphere.
The quiet, creeping nature of the Columbia tragedy is what makes it so haunting. That piece of foam, while being very light, was moving at a high relative speed when it struck the orbiter's wing. The impact had punched a hole, estimated to be about the size of a dinner plate, in one of the fragile, reinforced carbon-carbon RCC panels on the wing's leading edge. For the entire 16 days of the mission, this hole was a silent, unknown, and fatal breach in the orbiter's thermal armor. As Columbia hit the upper atmosphere during re-entry at over 20 times the speed of light, this small hole became the entry point for destruction. The superheated plasma of re-entry, with temperatures of thousands of degrees Celsius, began to stream into the interior of the left wing through this breach. Inside the wing, this jet of hot plasma began to act like a blowtorch, melting the aluminum structure from the inside out. Down in mission control, the first signs of trouble appeared as a series of strange and puzzling sensor readings. One after another, temperature and pressure sensors inside the left wing began to fail. At first, the controllers thought it might be a simple instrumentation problem. But as more and more sensors went offline, a quiet sense of dread began to build. They could see the problem spreading, but they couldn't understand what was causing it. Inside the cockpit, the crew was likely unaware of the danger until the final moments. They would have seen the sensor failures on their displays, but the shuttle was still flying perfectly on autopilot. Then, the failing wing structure began to create a massive increase in drag on the left side of the vehicle.
The autopilot had to fire the steering jets on the right side to compensate. In the final seconds of the data stream, the vehicle finally went into an uncontrollable roll. The immense aerodynamic forces then tore the orbiter apart, high over the state of Texas. All 7 astronauts were lost, just 16 minutes from their scheduled landing.
The investigation into the Columbia disaster was another moment of profound national mourning and intense scientific detective work. In the weeks and months that followed, one of the largest ground search operations ever conducted was launched across Texas and Louisiana. Tens of thousands of volunteers and emergency workers walked in lines through forests and fields, searching for pieces of the orbiter. They recovered over 84,000 pieces of debris, about 38% of the entire vehicle. This debris was painstakingly collected and taken to a large hangar at the Kennedy Space Center, where it was reassembled on a giant grid on the floor, like a colossal, tragic jigsaw puzzle. By studying this reconstructed wreckage and by conducting tests where they fired foam blocks at a replica of the shuttle's wing, investigators were able to confirm with certainty that it was the foam strike that had caused the fatal breach. The Columbia Accident Investigation Board, much like the Rogers Commission before it, concluded that the technical cause was again a symptom of a deeper cultural problem at NASA. They found that the agency's safety culture had, over the 30-year history of the shuttle, once again become complacent. The pressure to meet schedules, the normalization of small risks, and a communication breakdown between engineers and managers had all contributed to the tragedy. The board made a series of recommendations for NASA's return to flight, including the detailed in-orbit inspection of the heat shield on every future mission. But their report also had a more profound and far-reaching conclusion. It stated that the Space Shuttle, for all its amazing capabilities, was a fundamentally flawed design. It was a complex, fragile, and inherently risky vehicle. The board's final report was the quiet, somber recommendation that led directly to the decision to retire the Space Shuttle fleet once the assembly of the International Space Station was complete. The tragic, silent lesson of Columbia was that the era of the winged spaceship was coming to an end.
And so we arrive at the final, quiet chapter of our story. After another long 2.5-year grounding, the Space Shuttle returned to flight in 2005. The missions that followed were defined by a new, almost obsessive culture of safety and vigilance. The lessons of Columbia had been learned at a terrible cost. The most visible sign of this new philosophy was the now mandatory heat shield inspection. On the second day of every mission, the crew would use the long orbiter boom to conduct that slow, meticulous, full-body scan of their own vehicle. This procedure added a full day to every mission plan, but it was now considered absolutely non-negotiable. The data was beamed down to that large team of engineers on the ground who would pore over every image, looking for any sign of damage. The mantra was, trust but verify. Every single flight, no matter how perfect the launch looked, was treated as if it had a potentially fatal flaw until proven otherwise. The International Space Station also took on its new role as a safe haven. Every shuttle mission was now required to fly to the ISS. This ensured that if any irreparable damage was found, the crew would have a place to wait for a rescue mission. The shuttle would even perform a special maneuver as it approached the station, a slow, graceful rendezvous pitch maneuver, essentially a slow-motion backflip. This allowed the astronauts on the station to use powerful cameras to take hundreds of high-resolution photographs of the shuttle's belly, providing another crucial set of data for the damage inspection team on the ground. These final missions, From the return to flight in 2005 to the end of the program in 2011 were all dedicated to completing the assembly of the ISS. They were a series of quiet, professional, and successful construction flights. But with each mission, the sense of an era coming to a close grew stronger.
The final flights of each of the 3 surviving orbiters were historic and deeply nostalgic events. We have already talked about the final missions of Discovery and Endeavour, and that brings us, one last time, to the very final flight of the entire program, STS-135, flown by the orbiter Atlantis in July of 2011. The mission was a final critical logistics run to the space station, delivering a year's worth of supplies to ensure the station could continue to operate after the shuttle's retirement. The crew was a small, veteran team of 4. The launch was watched by millions, a final fiery farewell to this iconic machine, and the landing in the pre-dawn darkness of Florida was a moment of profound, quiet history. As Atlantis rolled to a stop on the runway for the last time, the mission commander, Chris Ferguson, spoke the final words of the 30-year program. "Mission complete, Houston. After serving the world for over 30 years, the Space Shuttle has earned its place in history, and it's come to a final stop." The silence that followed was the silence of an era ending. The great winged birds would fly no more. And so we come to their retirement, their final homes in museums across America. Seeing one of these orbiters in person is a truly humbling experience. They are so much larger than you imagine. They are not pristine models. They are weathered, experienced machines. You can see the scorch marks on their bellies, the thousands of delicate, individually numbered tiles, the sheer, mind-boggling complexity of it all. They are quiet, sleeping giants, resting after their long and incredible journey. They are a testament to an age of incredible ambition, a time when we built a machine that could ride a column of fire into orbit and then glide home in a graceful, silent fall.
So what is the final, quiet legacy of the Space Shuttle? It is a complex and a beautiful one. It was a machine born from a dream of making spaceflight easy and routine, and in that, it failed. It was more expensive and more dangerous than anyone had hoped. The tragic loss of 2 crews and 14 brave astronauts is a permanent, somber part of its story. It reminds us that the journey to space is never, ever routine. But the shuttle was also a machine of incredible triumphs. It was a scientific laboratory that conducted thousands of experiments. It was a repair vehicle that saved our beautiful eye on the universe, the Hubble Space Telescope. And it was the orbital construction truck that built the single greatest international project in history, the International Space Station. Without the shuttle's unique, massive payload bay, the ISS simply would not exist. And perhaps its greatest legacy is a human one. Over its 30-year career, the Space Shuttle program flew 135 missions. It carried 355 individual astronauts into space from many different countries, of many different backgrounds. It was the program that truly opened up spaceflight, making it more diverse and more international than ever before. It was a flawed masterpiece, an incredibly ambitious, beautiful, and inspiring machine that was also a constant, quiet reminder of the immense difficulty of what we are trying to do when we leave our planet. It was the bridge between the first exploratory steps of the Apollo era and our current era of continuous human presence in orbit. It was the last great glider. And now, its long mission is complete. It is time for it, and for you, to rest. Sweet dreams.